Okay, let's talk about Descartes' rule of signs. What does this do for us? We saw last time that whenever we have an n-degree polynomial, that polynomial is going to have n complex roots, right? And those roots can either be real or imaginary. If they're real, those real zeros correspond to x-intercepts, correct? All right, this Descartes' rule of signs helps us find those x-intercepts. And what it says, let f be a polynomial with real coefficients and a non-zero constant term. That's kind of important. The constant term can't be zero. We can tell how many positive real zeros we have, so positive x-intercepts. The number of positive real zeros is the same as the number of sign changes in f of x. So it's the same as the number of sign changes in the polynomial, or is less than the number of sign changes in the polynomial by a positive even integer. We can also tell how many negative real zeros that we have. It's the same as the number of sign changes in f of x, or f of negative x, or it's less than the number of the sign changes in f of negative x by a positive even integer. Let's go see how that's applied. The example says, find the number of positive and negative real zeros. There's the polynomial. It's a 5th degree polynomial, correct? And I've told you, since you have technology at your fingertips, what's the first thing you should always go do? Stick it in y equals and graph it, right? So let's go do that. I put it in the y equals. I hit graph. How many positive real zeros do you see? 3. It's a degree 5, so if it has 3 positive real zeros, how many imaginary zeros will it have? 2, right? And that makes sense because imaginary zeros always come in complex conjugate pairs. Remember that from last time? All right, what I want you to see is that there's 3 positive real zeros. F of x, you see here's a positive coefficient, a negative coefficient, positive coefficient, negative coefficient, positive, and then negative. So how many times did it change signs from positive to negative? It changed signs 5 times. So the number of possible positive real zeros will either be 5, or it could be 3, or it could be 1, because it had to decrease by a positive integer, even integer, correct? Okay, then it tells us to go look at f of negative x. If you plug in a negative x, everywhere you see an x in your original polynomial, anytime it's to an odd power, it changes the sign out front, correct? So this one would change sign to a negative. This one's not going to change signs. If you plug negative x in for x, negative x to the quantity 4 is the same as just x to the 4th, right? So that one does not change signs. But if you plugged negative x quantity cubed in, that would change to a negative 12 x cubed. Okay, when you look at the f of negative x, how many sign changes do you see? None. That means Descartes' rule of signs says there are 0 negative real roots. Question?
Can you go over that? So, what I understand is negative by every term, right? Is that what you're doing?
Hold on just a sec. Question was, how did I get this? So I went up to the original polynomial and plugged in negative x. So that gave me negative x quantity to the 5th minus 6 negative x to the 4th, 12 negative x cubed, and so on. You see that? Okay, when I do negative x to the 5th, that's the same as saying negative x to the 5th, because there were 5 negatives. which made the answer a negative, right? Then I had minus 6, negative x to the fourth. There's an even number of negatives, so it's just x to the fourth. You see it? No, because the original was a negative 6.
So what you're doing is you're multiplying the negative x, right? Negative x.
I have negative 6, negative x, negative x, negative x, negative x. So there's 1, 2, 3, 4, 5 negatives, which would make it a negative. Does that make sense? Okay. When I looked at f of negative x, there were 0 sign changes. So that meant that I have 0 negative real root possible. When I looked at the graph looked like this, yes? Oop. You agree? So how many positive real zeros did I have? Just 3. But what degree polynomial was it? It was an x to the 5th. So that means that I have to have 2 imaginary zeros. Sometimes you will see a sign chart like this. These are positive real zeros, negative real zeros, imaginary, and then total. From up here, how many positive real zeros could I have? I could have 5, 3, or 1. If I had 5 positive real, that would mean I would have 0 negative real, 0 imaginary, for a total of 5 zeros. We also saw from f of negative x that there were no negative reals, right? So if I have 3 positive reals, I have to have 2 imaginary for a total of 5 zeros. If I had had 1 positive real, I would have had to have had 4 imaginary for a total of 5 zeros. You may see this kind of a chart in your Connect Math. I want you to fill it in. Okay, question was, where did the 3 and the 1 come from? Came from right here. But where did that come from? Right here. It said the number of positive real zeros is equal to the number of sign changes, which there were 5, right? There were 5 sign changes here from positive to negative. Or it's less than the number of sign changes by a positive even integer. So I did 5 minus 2 and then subtract 2 again. That's where the 5, 3, 1 came from. Okay, for the next example, find the zeros and their multiplicities. I give you a polynomial of degree 5. Very first thing I'm going to do is go look at the graph. Put it into y equals, hit graph. How many positive real zeros do we have? 1. How many negative real zeros do we have? 1. It's a double multiplicity though, right? Because it touches. So that accounts for 3 zeros. So how many imaginary will we have? 2, because we have to have a total of 5. So here we go. I'm going to kind of put everything together in this section for you. First thing we're going to look at are possible rational zeros. You remember the form P over Q? So let's go look at possible rational zeros. They have to be of the form P over Q. P has to be factors of 18. Q has to be factors of the leading coefficient 1. Okay, possible factors of 18, plus or minus 1, 2, 3, 6, what else? 9, and 18. All over 1. Okay, how many possible rational zeros are there? 1, 2, 3, 4, 5, 6 times 2 is 12. If you did not have technology in your hand and you wanted to see if any of these are actual rational zeros, you would need to do synthetic division 12 times to see if you got a remainder of 0. We have technology. We don't have to do that. We went and graphed it, and we saw that the graph looked like this. So how many rational zeros did we see? 2. What were they? -1, so we hit trace, -1, enter, and we saw that yes, indeed, it is a 0. It also looks like maybe 2. Trace, 2, enter, yes, the y value is 0. So I'm going to go over here on my graph. This is at -1, and this is at 2. I just jumped ahead a lot, right? Because I cheated with technology. Do you want to see Descartes' rule of signs applied here? You see another example of Descartes walked through? What is my f of x? It was x to the 5th, 6x cubed, minus 2x squared, minus 27x minus 18. How many sign changes do you see? 1. That's it, right? There was just one sign change. So how many possible positive real roots will that function have? 1. 1 possible positive real 0. Or root. Now let's go look at f of -x. I would get -x to the 5th minus 6x cubed minus 2x squared plus 27x minus 18. How many sign changes do I see?
2.
Just 2, right? It goes from negative to positive to negative. So there's 2. So there's 2 sign changes. So we can have 2 or 0 possible negative real zeros. Now, how many do we actually have? 2, because that's a multiplicity of 2. So do you want to see the sign chart on that one for Descartes? All right. So we have positive real, we have negative real, we have imaginary, and total. What did we say about positive? We could just have 1, right? But with negative, we could either have 2 or none. What's the total? 5. So we either need 2 imaginary or 4 imaginary. 1 real plus 2, 1 real positive plus 2 real negative plus 2 imaginary would give you 5 zeros. Which one do we know is the right choice? The first one, because we looked at the graph. Okay, I know what this one is. It's x equal 2. I know what these are. It's x equals negative 1. How do I go find my two imaginary? I've got to go do synthetic division and whittle the polynomial down. All right. So what is my polynomial? X to the 5th. I don't know it. Plus 0x to the 4th plus 6x cubed minus 2x squared minus 27x minus 18. Is that right? Yep. And I want to do 2 as my 0. All I did was put the coefficients of my polynomial and my 0. Go do it. Eighteen times 2 is what, 36? Did synthetic division verify that x equal 2 is a 0? Yes, because I got 0 for the remainder. What was my negative rational 0? Negative 1. Go do it. Bring down the 1. 1 times the number in the half box is negative 1. Add them going down. 1 times the number in the half box, add them going down. 9 times the number in the half box, add them. 9 times the number in the half box. Was negative 1 a 0? Yes. And we saw that it had to have multiplicity 2 because when we looked at the graph, what did the graph do at x equal negative 1? It touched. It did not cross. So we know that it has to have even multiplicity, meaning that we can pull it out again. Drop the 1, negative 1, 0, 9, negative 9, 0. Yay, it worked again. Could you write f as a product of factors now? What are the factors? X minus 2, x plus 1 quantity squared, x minus 2, x plus 1 quantity squared times what? X squared plus 0x plus 9. How did I get the x squared plus 9? This was an x to the 5th polynomial. This became an x to the 4th, x cubed, and x squared. Every time you take a 0 out, you reduce the degree of the polynomial by 1, correct? So this became 1x squared plus 0x plus 9. Could you set all those factors equal to 0, solve for x to find all 5 of your zeros? Yes. We know that x equals 2 was a 0. We knew that x equals negative 1 was a 0 of multiplicity 2. So it counts twice. What if we set x squared plus 9 equal to 0? So x equals plus or minus root 9i, right? So x equals 3i and x equals negative 3i. We have found all of our zeros. We were supposed to find the zeros and state their multiplicity. That multiplicity is 1, this multiplicity is 1, and this multiplicity is 1. Before you even started working this problem by hand, how many of the zeros were you able to find using your calculator? 3. Go synthetically divide those 3 zeros out, see what you're left with, and find your imaginary ones.